So there's an abstraction of this. It's a more general. There's an abstract.
Yeah, you can take any automatic, any operator. That's just make a thing. Okay, you can sigma y or sigma anything. You can take anything. And then now I can define what means cyclic thing. This means the cyclic. I call it cyclic pair. Maybe there's another. So the cyclic pair actually is just a two rational function. So they satisfy the following condition. So this is a cyclic. Apply to some. You take any rational function. With that, definitely we will need an assumption. Then you think about this special formula. So you know the meaning of this formula, right? And then we need the assumption that actually the h is not actually rational function. They satisfy the following condition: sigma s h equal to sigma y t and h. So you can think about this just a shift with respect to x, this shift with respect to y. I just want to make try to unify this q shift and the shift case. That's why I use sigma x. And then you can easily check that once this is because sigma x commutes with sigma y, and this is true, the three condition. Actually, you can check that when you think about this sigma x f minus 1, this is the difference x of f. You want to verify whether this is a doublet pair, right? You need to calculate this, compute those things. But you see, this is the f. This actually is sigma x minus 1 applied to f. When you do this sigma x minus 1, you cancel out with this. So what you get is sigma x s minus 1 applied to h, and this is equal to sigma x s h minus h. And on this side, this is sigma y minus 1. This also cancels out with the denominator. But actually, that's this is what I do is formally. But in fact, you need to really use this definition to verify. Anyway, let's make it the same here. And g minus g, and then you get the sigma y t h minus h. By assumption that sigma h satisfy this condition, so they're equal. That's kind of where you can cook up the very non-trivial solution of this equation. I call this is called the cyclic pair because really you go s and then go run. So that's kind of like cyclic. So like s, x, and now selection is y, t, so you get cyclic. So now the theorem is that theorem which I prove that that's all possible pairs, and any pair will be linear combination of exact one and this cyclic one. So let me write down the theorem.
So there's an analog of the continuous case.
Yeah, but it's non-trivial analog.
Yeah.
It's taking me like half year
Yes.
to figure out what's the analog of this log derivative.
Yeah.
Because I need to write. After this, why I dedicate to borrowing. Another reason is in 2006, 2 years ago, I also met Neil in a conference which organized by John, and then he invited me to give a talk. I give a talk about the W method on the W conjectures, and sadly, and after this conference, just 2 months after the conference, he passed away.
Yeah.
So and then Fields Institute organized a book dedicated to him, and then he invited me to write a paper on this topic. So naturally, I try to work on this. Now the theorem is that.
So can you deduce the continuous case from your framework? Can you bring it all together?
Sure.
Yeah.
There's
limiting case.
We need unified all the cases.
So in particular now you can also have a new proof of the thing from 1990.
Yes.
Yeah.
With Christoph. So.
Yeah.
Yes. Yeah. Indeed, we use.
So it's a very unified approach.
And for the theorem, this for the shift case, and we have the following theorem. If f is a pair of it, then if and only we can show that actually this then exists a b1 equal to bn is a Gaussian function here such that so f can be written as. So this is trivial pair, right? This is trivial pair. This you don't need to care about this pair. And then after that is the interesting thing, is linear combination of a cyclic pair. Apply to bi. you don't need to specify C because the constant can be moved into this B, so I don't write the C here. But then in the differential case, I write C, but you don't need to do this. The Ti apply to Bi. And then those Bi is not arbitrary rational function, they satisfy the X, Si, Bi is, for each I, they satisfy the following condition, Ti and Bi. And for I, 1 to n. So that's the structure of the rational W pair in the shift case. So informally, this theory just say that any W pair in shift setting is the linear combination of the exact pair, trivial, and then the linear combination of secret pair. That's something like the differential case. Something pattern is very nice. So that's the structure of this. And then you can write down all possible W pair because you pick any rational, and you can take, and there's a classification of all possible rational functions set by this condition. You can, this is the, there's a, in our paper we also calculate all possible rational functions of set by this kind of condition. And then you know how to hook up all possible rational W pair in this. And also then there are some also mixed case, right? If there's something is derivative, something is shift, but then in this case even simpler. So let me show you. Because I have time, so maybe I can take one example. Let's see. It's nice to have one example. So let me take one example before I go into the last case, the missed case. So, but the example actually just help you to remember something. So you can take a P equal to 2x plus 3y. So you can notice that P satisfies the sigma x mean sigma x means shift to the x means sending x to x plus 1, and sigma y will be mean. So you can see this is you shift x by 3. This is equivalent to shift y by 2, right? So this is you get this is exactly this condition, and then you can cook the secret pair. So you can, you can just take a 1 over p plus 1 over sigma x, or you can take a, sorry, next thing either. Let me just write this. You can write p plus sigma x p until 3 minus 1. Sigma is 2p, and then this is a p plus sigma y p. And then you can verify that actually this is a pair sigma y minus f equal to sigma y p minus 1. You can, anyway, that's just a simple example. You can cook up a lot of different pairs, and you can also check that maybe you can find some nice, which is 1 over p, something like this. Then you can get something like series, acceleration, different formula. After you have anything you want, you can, this is like a mile. You can dig into, you can get many different materials, some gold or maybe something kind of rubbish. But anyway, you can find different material from this thing. So that's why I focus on the structure things. Now let me go to the last cases. Maybe today I can finish my talk before the time. So the third case is the missed case. So missed case is just mean some, so we have the equation. So now the partial x you can take as the shift or Q shift, and then the partial y is just the derivative with respect to y. Derivative with respect to y. And in this case, exact pair is also this is always the same. It's easy, and just keep writing these things. Don't you get bothered, but you will. And theta, I just say so let me write this is a theta x minus 1. This is the theta as a minus a. This is a, you see, this is a shift and this is the relation. That's why you call it mixed, because this is a discrete, this is a continuous. That's the mixed thing. This is the exact pair, you can easily verify. And then there's a funny thing I call the trivial pair. This is also trivial, but in the mixed case there's nothing interesting. Actually, there's one trivial thing is that you take f is free of y, then this equals 0. And g is free of x, then this is also 0. 0 equals 0. So you can take one trivial pair is just f in this cx, and g is in, sorry, gy is free of, and then is cx. This is really a trivial, not interesting thing. And the theorem I prove actually is that's all. That's everything is trivial in this case. That's, maybe I feel disappointed, but that's the line.
So it's a non-trivial theorem.
Yeah, basically everything is trivial. Indeed, the proof is not so trivial. So that sometimes I make a joke with students that sometimes I give you a problem and you find that it's trivial, but then you to prove that it's trivial is maybe this.
Yeah, non-trivial is trivial.
Yeah. Then if this is satisfy this equation, sorry, it's possible. And then we show that actually there exists the h in any partial function, and u is trivial, cy, v, and cx. And then such that f is equal to cy, h, cx, h, minus h plus u plus v. I mean, that's what I say. Basically, I already mentioned any pair actually in the mixed case is very trivial. Sum of two trivial pairs. So that's the all possible theorem. That's basically I finished all the things about the rational case. So let me say something which is I'm going to work on is definitely I need to go beyond the rational case. And then I just say something about how we can go beyond this rational case and what's the next question. So now everything is fine in the rational case, and we have we found all possible solution, all possible rational double pair. Now we go to more interesting case. But I will just say some words and not trying to write down. I didn't find for the moment any theorem, so I only have some idea. So now we go beyond the rational case, but still we don't want to be the problem not so tractable. So the idea for the next question is the next goal. We want to think about f and g are hypergeometric, which is very interesting for getting a combinatorial identities. What's to mean the hypergeometric over a rational function? This is over a rational function field. So this is one of the non-trivial class of function which is more general than rational function. So the definition of this is just you shift this. So this is, and then you take the quotient of the shift and the f itself, and then because there are two variables, you can also shift with respect to y. If both are rational functions, then we call this hypergeometric thing. And this is actually very useful. Many binomial coefficients is of this type. So that's why this class is very interesting. Actually, those two functions, we can say this A and B, they are not, you cannot say, I can assign arbitrary A and arbitrary B. There are some compatible condition between A and B, because usually we need a function like if you shift x first, then shift y, this should be equal to shift y first and x. So this can derive some, this means A and B actually satisfies the equation, which is the following equation. So you just, this comes from this, and this is, you first conjecture this shift using the first one, and then you can use the second one, and then you can do this first, and then this first. So anyway, you can get the condition for A and B, which is the following. This is A 6y plus 1 over A plus y equal to B 6 plus 1 y over B 6y. So this is a condition satisfied by this A and B. And there is a classical theorem which is called Ori-Sato theorem. Is due to Ori and Sato. So this is the two very famous people. So this is called Ori-Sato theorem. I will not write down this. The Ori-Sato theorem is similar like what the structure theorem I give. So they will characterize all possible A and B such by this condition. That's I will not write down the formula. It's something like what I write. You can find some trivial solution of this typical solution, then you prove that actually anything can be product of those typical solutions. That's the Ori-Sato theorem. And the motivation of the Ori-Sato is that the proof of this that you know that for hypergeometric function, if a sequence in the universal case, actually you can prove that in universal easy. So any hypergeometric term can be written as a product of rational sequence and some gamma function. You can write it. Then with Ori-Sato, actually, the pattern in the universal case is still true in the multivariate case, which means any multivariate hypergeometric term can be also written as product of rational sequence times some gamma functions. So gamma function satisfy this is hypergeometric. That's the corollary of Ori-Sato. And then so now basically we know the structure of the object we want to study. So we know the structure of this. And then what I want to, because I want to solve this equation for f and g, both are hypergeometric. So now I understand the structure of this f and g. Now I want to, but the structure is for arbitrary hypergeometric. But then if they satisfy a condition, which means inside the structure you need to profile, get a, how to say, you inside the structure you have a substructure. So you need to make this use this equation to do something. For the moment, the only thing I can prove that is the following. So using the idea from the idea of collinear telescoping, actually you look at this equation. Actually, in terms of the terminology of collinear telescoping, this just means that partial x is a telescoper for f with respect to y. So this just means the W equation is a very special telescoping equation. Just to mean telescope is this special thing. And I know that we know that actually if a hypergeometric term has a telescoper, and this term must be very special form, which is called Abramov. Abramov's criteria. Criteria say that what's the meaning of a telescope? Just mean so this by Abramov criteria we can say that if in the shift case if f a hypergeometric term, if satisfy this kind of condition, then f must be a delta y certain another form plus some another kind of like a remainder, and then what we can by Abramov criteria we can show that R must be in proper form. So proper form is just a polynomial times some product of a gamma function. This is defined in your paper in 1992. I think you introduced called proper hypergeometric terms. And then using this criteria, now we can reduce the general hypergeometry, the problem in the general hypergeometric case to the proper case. You only need to study the proper case. And then I have 1 minute left. So the next thing you can do, go beyond the rational case. You need to fix some kernel. This is the like n choose k. Now the next question is, the problem is to characterize all possible polynomial such that the difference of this is the difference of another g. So that's the problem. Now question is fix this like n choose k, because this identity is, you know, this leads to this 2n choose n. And then the question is to ask whether we can add something here by the polynomial Pn, still get the identity nicely. So that's the question, how you can characterize this rational, not the polynomial in n and k such that they satisfy. There exists another g which is still hypergeometric. And then I'm now working on this. If anyone interested in this, it would be nice to do. This is like go beyond the rational case. So the rational case you can view as 1 over some denominator. This is just to take this spectral kernel. Now you need to characterize this polynomial, and that's the problem I'm working on. For the moment, I have no theorem, so I have some idea how to bound the degree or something like this. That's all I can say now. Thanks very much. So.
Thank you for doing all the rational WD that exist. It's very nice and very nice ideas. Shaoshi will be glad to answer questions in private, and we're gonna take all the speakers.